The last special type of sequence and series we're going to go through is what's known as geometric. So like arithmetic, we had a way to get from one term to the next by adding the same number. A geometric sequence is going to be found by multiplying the previous term by a number. So that number is going to be r. So the n plus 1 term is r times the previous term. So you can kind of see if you take the n plus 1 term divided by the term before it, it's going to equal r. So we call r the common ratio, because the common ratio between any two is r. So let's go ahead and find the common ratio of the geometric sequence. So we've got 1, -4, 16, -64, and that continues on. So since this is geometric, you could take the ratio of any two as long as it's 1 divided by its previous term. So I could take the fourth and divide it by the third, so a4 over a3. I could take the third divided by the second. I could take the second and divide it by the first. All of these will equal r. So you can see if I go through and do that, the fourth term divided by the third is -4. If you take the third and divide it by the second, that's 16 over -4, -4. Or the second over the first, still equal to -4. So your common ratio is -4. So this is one, although it is defined recursively, in the same way we could come up with a nice explicit formula for an arithmetic sequence, we can do that with a geometric sequence. So we're going to go through the process of finding that general term. So you have to start with a given quantity. I begin at a1. My second term is my previous term times r. My third term is going to be my second term times r. But I know what a2 is, so I can go ahead and replace it by the formula for a2. So it's equal to a2 times r, so you really have an r squared. If I go to my fourth term, it's my third term times r, and my third term is a1r squared. So that's equal to a1r squared times another r. So you get r cubed. So you can kind of notice a pattern. You start at a1, the value of r is 1 less than the index itself. So the general term will be an. It's going to equal a1 times r to the n minus 1. And again, this really holds for any term, because if you plug in n equals 1, you would get r to the 0 and just get a1. So this is our explicit formula. So now, given my first term and given that common ratio, let's find the general term and let's find the 14th term. And I don't need to go through and figure out all 13 terms before it. So my general formula is this. We go ahead and replace a1 by 17, and your r is 2. So you get 2 to the n minus 1. So if you want the 14th term, that'll be 17 times 2 to the 14 minus 1. Just 17 times 2 to the 13, which is a very large number. It's 139,264. Okay. So now, if we go ahead and sum this up, we are going to get a series. And this is a special one. We're actually going to be able to find the sum of an infinite geometric series. In all honesty, it's even nicer than the finite one. So the sum of the first n terms of a geometric sequence is called a geometric series. So you're going to sum up from k equals 1 to n of that general term. So it's the first term plus the second, third, keep going, your second to last, and your last term. We're going to add these all together. Now the arithmetic one is a little bit hard to show where that formula comes from, but we can actually show the nicer form for the sum of a geometric series. So let's go ahead and look at this general form Sn. What I'm going to do is I'm going to take every single term and multiply it by -r. So I'm going to look at -r times Sn. So your very first term a1 gets multiplied by negative r, so it's going to get lined up with the same power. So you get negative a1r. The second one times negative r is negative a1r squared. Keep going. If you take this term and multiply it by r, it's going to bump that power up by 1, so it'll be to the n minus 1. And likewise, if you take this, bump it up by an r, you're going to get r to the n. And so there's a term in the middle that would be right before this, right here. The n minus 3 power would have an n minus 2 power. So by doing this, you might notice now a lot of things are going to end up canceling. So these two cancel, these two cancel, a bunch of stuff in here is going to cancel, these ones cancel, and these ones cancel. So it causes everything to disappear when we add them together, except the first and last terms. So on the left-hand side, we get Sn minus r times Sn, and we're left with a1 minus a1r to the n here. So our goal is to find what Sn is. Go ahead and factor that out. You get Sn times 1 minus r. And then you can also factor an a1 out here. So now, just dividing by 1 minus r gives us an explicit formula for the sum of the first n terms. The only stipulation is you don't want that common ratio to be 1, because then it's going to cause 0 in the bottom. And really, if the common ratio is 1, I take the first term, multiply by 1, multiply by 1, multiply by 1. It's going to be really boring. It's just a constant sequence. So the sum is going to be the number of terms times that constant. Okay? So let's look at an example, and we're going to find the sum of this finite geometric series. And so I'm not given this in sigma form. I can't immediately tell you what this value of n is going to be up here. You can pick off a1 and you can pick off r, but n is a little bit more difficult. So we know the first term is 1, and if you look, you're multiplying by 1/3 every single time. So my common ratio is going to be 1/3. So if you were thinking of your general term, it would be a1 r to the n minus 1. So it's 1/3 to the n minus 1. So if you look at this sum, this exponent here is really your value of n minus 1. So if you plugged in n equals 11, that would give you 3 to the 10th. So this tells me my n is going to equal 11. So it's a sum from I equals 1 to 11 of 1/3 to the I minus 1, because that's our an. And you can double check. If you plug in I equals 1, you're going to get 1/3 to the 0, which is 1. If you plug in I equals 11, you're going to get 1/3 minus 10, which is our last one as well. So now I can go ahead and just utilize this formula to figure out my value of Sn. So it's going to be the first term times 1 minus r to the n over 1 minus r. So we're dealing with S11. It's going to equal a1 times 1 minus r to the n over 1 minus r. So now we just need to go through simplifying this. You could just plug it directly in a calculator, but I'll show you how to simplify it by hand as well. So this is going to equal 1 minus 1/3 to the 11th in the top. In the bottom, that becomes 2/3. So if you do 3 to the 11th, you're going to see that's 177,147. Dividing by 2/3 is the same thing as multiplying by 3/2. Doing this subtraction, you're going to get 177,146 divided by that denominator times 3/2. And then you can go ahead and simplify and find those common factors. The sum of this will equal 88,573 divided by 59,049. Okay. So now we can actually go through and talk about an infinite geometric series. So in this one, I am going to sum up an infinite number of terms And based on that common ratio, it can actually equal something. So we sum up from I equals 1 to infinity of that general term. And we're going to utilize the fact that we know when you sum up a finite number of values, what that's equal to. So if that common ratio is less than 1 in absolute value, you can see this value up here is the only thing that deals with the number of terms. Constant, 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 constant. This is the only variable. So if that common ratio is between -1 and 1, think of 1/10. 1/10 to the millionth power would be super, super tiny. -1/10 to the billionth power, super, 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 super tiny. So what happens is r to the n will go to 0 if you have some number between -1 and 1 as you add more and more terms. So that partial sum would approach a1 times 1 minus 0 over 1 minus r. So basically this will disappear as n goes to infinity. So it'll equal a1 over 1 minus r as you let more and more terms from your series into the sum. So if that common ratio is something between -1 and 1, this will actually equal something. If your common ratio is bigger than 1, however, think of your common ratio being 2. You're going to have your first term, multiply it by 2, multiply it by 2, multiply it by 2, multiply it by 2. And you're going to add all of those up. Those terms are just going to get larger and larger and larger and larger. So this r to the n is going to end up growing without bound. Even if it's like -2, it's still growing larger and larger and larger overall. And it's even oscillating between positive, negative, positive, negative. So really, it's not going to have a finite sum because those values, when n is like 1,000,000, 1,000, anything, is going to be so large. So it will not have a finite sum. If your common ratio is 1 or -1, same thing's going to happen. It's not going to have a finite sum. Because really, if your common ratio is 1 and your first term is 2, you're going to add up 2 over and over and over and over and over and over and over again. That's not going to be something finite, so you can't do it. If your common ratio is -1, it's just going to alternate between the same number being positive, negative, positive, negative. Stuff's going to cancel, but when does it end? It never does, so it's not going to be a finite sum. So ultimately, this infinite sum is going to equal a1 over 1 minus r when that common ratio is between -1 and 1. So this formula is only going to work when this happens. This does not happen, you cannot use this formula. And so that leads to an idea of series about convergence and divergence. So if the sum of an infinite series approaches a single finite value, so the sum equals something, we say the series converges. If the sum does not approach a single finite value, it diverges. So it either blows up to infinity, negative infinity, or it just doesn't equal anything at all. Okay. So let's look at 2 examples. Let's find the sum of the series if possible. And so we want to see what is this geometric series, and all we need is the common ratio for this and that first term, because this is going to infinity. So let's go ahead and plug in a few values of n just to see what a1 and r are. So when you're going to plug in n equals 1, n equals 2, and n equals 3. When you plug in n equals 1, you get a half. Then you get a half squared, a half to the third. So this is a half plus a fourth plus an eighth, and it continues on forever. So your very first term is a1, that's a half, and your value of r is also a half. So since the absolute value of r is less than 1, we can say this series converges. And further, we know what it converges to. It converges to a over 1 minus r. That's a half over a half. This thing ends up equaling 1. So the sum from n equals 1 to infinity of 1 over 2 to the n is equal to 1. Right? So let's do one more example. we've got 6 over 5 to the n minus 1. So really, this is going to be that indication it's geometric. And really what's inside there as your base of the exponent is the common ratio. But if you're never 100% sure, just plug in some values of n to see what those are equal to. So if you plug in n equals 1, you get 6 over 5 to the 0. N equals 2 is 6 over 5 to the first, then 6 over 5 to the second, and it keeps going. So this is 1 plus 6 over 5 plus 36 over 25, and it continues on. So since A1 is 1 and your common ratio is 6 over 5, we can say, because that common ratio in absolute value is bigger than 1, the series diverges. So it has no sum. You're done. This doesn't equal anything at all. So as soon as that common ratio is bigger than 1 in absolute value, you're finished. You don't have to do a single thing from there. Okay. So the last thing we're going to do is we're going to see an application of something that's geometric in real life. So you might be guaranteed a certain raise every single year, whether it's for cost of living, you get a 1-cent raise. This person's going to get a pretty hefty raise each year, but it's all going to boil down to it being a geometric sequence. So a company offers Jordan a starting salary of $22,000 with a guaranteed 15% raise every single year. What will her salary be after she's been with the company 10 years? So since she's increasing by 15%, getting her previous salary plus that, we're going to go ahead and take her current salary and multiply it by 1.15. So that's 115%. She keeps her old and she gains this extra 15%. And that's exactly a geometric sequence, because her second year, she would get 115 the previous one. Third year, she gets 115% of the second year's salary. Fourth year, 115%. So it's just a geometric sequence. So your first term is 22,000, that's her base. And every single year, you multiply again by 1.15. So the nth term is the first one times r to the n minus 1. So that's 22,000 times 1.15 to the n minus 1. So if we want to see how long it's been after 10 years, we'll go ahead and plug in A10. So it's 22,000 times 1.15 to the 9th. If you plug that in, her salary is going to be $77,393.98. And if she stayed there another year, she'd get another 15% raise. You multiply by another 1.15. So these have really nice applications in terms of finance too. If you think about interest formulas, those are really just geometric sequences, because you're taking a previous balance, timesing it by an amount. So all those formulas we've already seen are just specific applications of geometric sequences.